Hi, and welcome to the lecture on statistical linear regression models as part of the Regression Modeling Coursera course, which is part of our data science specialization. My name is Brian Caffo, and I'm a professor in the Department of Biostatistics at the Johns Hopkins Bloomberg School of Public Health. The class is co-taught by my co-instructors and colleagues Jeff Leake and Roger Pang. Finding a good regression line using least squares is really simply a mathematical procedure. However, we'd like to do statistics. We'd like to draw inferences based on our data. In other words, we'd like to generalize from our data to a population using statistical models, and that's what we're going to talk about in the statistical linear regression lecture today. So let's consider our probabilistic model for linear regression, and we're going to start with one of the most simple ones. Our response yi is our line beta naught plus beta 1 xi, where we don't know beta naught or beta 1. These are the population parameters that we would like to estimate. Xi is a collection of explanatory variables that we do know. And then to make it a statistical model, we're going to add Gaussian IID Gaussian errors, which I'm going to denote epsilon I. So the epsilon i's are going to be assumed to be normal mu sigma squared. There's a lot of different ways to interpret these independent errors. Perhaps one of the easier ones is to think they're the accumulation of a lot of variables that you didn't model but maybe should have, that act together on the response in a way that can be modeled as if independent and identically distributed Gaussian errors. However, let's put these kind of difficult interpretation issues aside for the time being and simply talk about how we mechanically work with statistical inference for regression. I would note that the expected value of the response given a particular value of the regressor is simply the line at that regressor, beta naught plus beta 1 xi. And the variance of the response at any particular value of the regressor is sigma squared. This latter point, let me elaborate just a little bit. This is the variance around the regression line. This is not the variance of the response. So it will be lower than the variance of the response by itself because you've explained away some of the variation with x by conditioning on x. I would also note that both this expected value and the variance are population quantities. They have sample analogs that we'll estimate, but right now these are population quantities. These are the estimands that we would really like to know.